Hi all, in the last class we have discussed spanning sets, definition of the spanning sets and some examples for a spanning sets for a vector space V. Now we can define a basis of a vector space. This is the definition. A basis for a vector space V is a set of vectors that is linearly independent and spans V. Now we look into some examples. If you consider R2, R2 is represented by uh, these vectors A, B, such that A, comma B are real numbers. So this is the representation of R2. R2 can be represented as a matrix, 2 by 1 matrices. Then you can say that if we write this set, I call it as B. B is the set of all vectors 1, 0 and 0, 1. Okay, these are the two vectors. This of course this is a subset of R2. Now you can easily verify that this B is a basis for R2 because in order to verify this, we verify the spanning property of this set. That means if you take any AB from R2, you can write this AB as a linear combination of 1, 0 and 0, 1. Okay, when you write AB is equal to A times 1, 0 plus B times 0, 1. So this can be written as, this can be set as a linear combination of the vectors of the set B. Okay, so B spans R2. Now we can, so this is the what is the implication of this? From this you can say that B spans V, or B is the spanning set of V. Now we can verify the linearly independence of these vectors. For that we assume the linear combination C1 times 1, 0 plus C2 times 0, 1 as a 0 vector. We will prove that these coefficients C1 and C2 are 0. So this implies when you add the left side, you can get this is the vector C1 C2 equal to 0, 0. From this you can get C1 equal to C2 equal to 0. This shows that the linear combination, the only possible linear combination which yields 0 is C1 equal to 0, this corresponds to the C1 equal to 0 and C2 equal to 0. So this shows that the set B is linearly independent. Linearly independent, hence it is a basis. B is a basis for V. Another example is if you consider P3, we have already discussed the vector space P3. This consists of set of all polynomials, set of all polynomials of degree at most 3 and the zero polynomial. We cannot define the degree of the zero polynomial, that's why we include zero polynomial in the set as a separate entity. So this is a vector space. Now if you take any consider a set, a subset of this P3, 1 t t square t cube. So this is a subset of P3. Then you can say that the set is linearly independent and spans P3 as well. So if you take any arbitrary element of P3, say a0 plus a1 t plus a2 t square plus a3 t cube, this is a general element of P3 belongs to P3. You can say that this element is a span of this a naught can be written as a naught times 1. So this implies the set B spans P3. because any arbitrary element can be written as a linear combination of 1 t t square t cube etc. 1 t t cube 1 t t square t cube. Okay, so that is these are the elements of P. Now we can verify the linear independence. So if you assume a linear combination is 0, say C0 plus C1t plus etc., or I like C2 t square plus C3 t cube equal to 0. So 0 is a 0 polynomial, implies each coefficient C0 is equal to C1 is equal to C2 is equal to C3 is equal to 0. So this implies B is linearly independent. So this is also a basis for P3, linearly independent, hence it is a basis. Hence B is a basis for P3. Okay, now we have a problem. Determine whether the set C, this consists of vectors t square plus 2t minus 3, t square plus 5t, this is the second element, 2t raised to 2 minus 4. So this contains 3 polynomials of degree 2. Of course, this is a subset of P3. Okay, we need to verify that the set C is a basis for P3. Okay, so this is the answer is trivial. It's not a basis. It's not a basis because the reason is very simple. If you consider if it will the set is a basis, then you can the C spans P3 and C should be linearly independent. So these are the conditions for the properties of a basis set. So basis element. So and when you consider a third degree polynomial, say t cube belongs to P3 because P3 contains all the polynomials of degree at most 3. So T3 is T raised to 3 is a T cube is a polynomial in P3. Then you cannot write T3 as a linear combination of these polynomials. Okay, so you cannot find A, B, C the scalars such that A times T square plus 2T minus 3 plus B times T square plus 5T plus C times 2T square minus 4. Okay, so we cannot find such a coefficients ABC because the left side is a third degree polynomial and right side is a second degree polynomial. So you can never equate a third degree polynomial to a second degree polynomial. So this will be a contradiction. That means there is no such coefficients ABC. Therefore, we can say that the set C is not a spanning set. Spanning set for the vector space V. The vector space is here. The vector space is P3. So C is not a basis. C is not a basis. Next, we have another problem. Determine whether the set B consisting of the vectors 1, 1, 1 minus 1 is a basis for R2. Is a basis for R2. R2 is nothing but R2 is represented by taking 2 by 1 matrices AB such that A comma B belongs to R. Okay, so we have to verify whether this B is a basis. So first we write this AB. We need to prove that this B is a spanning set and B is a linearly independent set. So first we have to verify the spanning property of B. For that we assume an arbitrary element AB belongs to R2 and we need to find out coefficients D1 and D2 such a way that D1 can be D1 times this 1 1 plus D2 times 1 minus 1 should be AB. Okay, we need to find out the coefficients d1 and d2 such that this holds, okay, which satisfies this equation. For that, we simplify the right side. Then you can get this. The first quantity is, the first term is d1 plus d2, and the second entry is d1 minus d2. Okay, so in order to get d1 and d2, we need to solve the equations. d1 plus d2 is equal to a, and d1 minus d2 is equal to b. So this together imply that 2 times d1 is equal to a plus b by adding these two equations. Consequently, d1 should be the half of a plus b, so a plus b by 2. And similarly, you can get, by subtracting these two, you can get d2 as a minus b by 2. Okay, so these are the values of d1 and d2. That means AB can be expressed as a linear combination of 1 1 and minus 1 1 minus 1 by taking d1 as a plus b by 2 times 1 1 plus the other coefficient is a minus b by 2 times 1 minus 1. When you add this, you can get a in the first component and b is in the second component. Okay, so this implies B is a spanning set. Now you can verify the linearly independence. Then we assume the linear combination C1 times 1 1 and C2 times 1 minus 1 equal to 0. 0 means here the vector space is a 2 by 1 matrices, that is R2. Then the 0 represents, the 0 means the additive identity of that vector space, that is 0 0. Then consequently we have two equations, C1 plus C2 equal to 0 and C1 minus C2 is equal to 0. This together imply that C1 equal to 0 and C2 equal to 0. Okay, so this shows that B is linearly independent. Therefore, B is a spanning set as well as a linearly independent set. Hence, it forms a basis. Hence, B is a basis for V. V is our R2 here. So we can say that this B is a basis for the vector space R2. Now we have a couple of definitions. First one is finite vector space. A vector space V is finite. This is finite dimensional vector space. First we can define finite dimensional vector space. A vector space V is finite dimensional if it has a basis, it has at least one basis. Okay, it has a basis containing a finite number of vectors. Containing a finite number of vectors. This is the definition of a finite dimensional vector space. Example, R2. We have shown that R2 has a basis B consisting of vectors 1 0 and 0 1, and R2 has another basis of vectors 1 1 and 1 minus 1. So the basis should not be unique in any case. So if a vector space may contain more than one basis, distinct basis. So R2 is a finite dimensional vector space because it has a basis consisting of two elements. Okay, so it contains a finite number of elements. Therefore, R2 is a finite dimensional vector space. Similarly, P3 is a finite dimensional vector space. We have shown that it has a basis consisting of the vectors 1 t, t square, t cube. So this P3 is also a finite dimensional vector space because it contains a basis consisting of 4 vectors. Okay, so this R2 is a finite dimensional vector space because it contains a basis consisting of 2 vectors. The other definition is infinite dimensional vector space. Okay, that is nothing but all vector space which are not finite dimensional. Those vector spaces are called infinite dimensional vector space. A vector space that is not that is not finite dimensional. Dimensional is called infinite dimensional. Infinite dimensional vector space. These are the two definitions. As a remark, we can write finite vector space. Remark, that is finite vector space. A vector space is said to be finite if it contains only a finite number of vectors. Okay, V is a finite vector space if the cardinality of V is finite. Hash V is called the cardinality of, this is what we called the cardinality of V. So in order to define the finite dimensional vector space, we need to verify the cardinality of the bases. In order to get the finite dimensional vector spaces, we need to verify the cardinality of the vector space itself. Okay, so the dimension depends on the basis set, and the cardinality of the vector space will give the finite vector space. So infinite vector space is nothing but the vector space V containing more than containing no finite number of elements. Okay, that means it contains infinitely many elements. Okay.